I want you to picture a scene with me for a second. It's late. You're in this dimly lit sushi place in the city.
The kind with the good sake.
Exactly. The jazz is sog, you've got that moody amber lighting. It honestly feels like the start of a noir film.
A meeting between two spies, maybe? Or a handover.
It does, but the stakes here are, well, arguably higher if you're the one trying to keep production servers online.
That's very true.
So we are digging into a source we found called the Axiom Paradox. And the two people at that table, they're not detectives. We have Marcus, who's this brilliant software architect, the big picture visionary type.
And then sitting across from him is Elera. She's the operational genius, the one who gets the pager alert at 3 in the morning and has to actually keep the lights on.
It's that classic dev versus ops dynamic, isn't it?
The architect versus the mechanic, yeah. But they're co-founders, and you can just feel the tension.
And here's the core conflict. Marcus has just launched his masterpiece, a system called LEMORA v4.3. He's so proud of it. He calls it axiomatically perfect.
Which is a brave thing to say in software.
It really is. He's built it on these 6 unbreakable behavioral contracts. He thinks he's basically solved deployment for good.
And using the word perfect is usually just an open invitation for the universe to send you a catastrophic failure.
And that's exactly what happens. Elera, she pours him a sec, she looks him dead in the eye, and she drops the bombshell.
The system has 7 critical bugs.
7. But here's the twist, and this is why we're doing this deep dive. She doesn't say his design is wrong. In fact, she says the axioms are beautiful.
Right. And that is the mystery we need to unravel here. How can a system be perfect in theory, but completely broken in practice? This is what they call the implementation gap.
The gap between the whiteboard and the keyboard.
Exactly.
So our mission today is to debug that gap. We're going to look at LEMORA, we're going to break down these failures, which I think a lot of you listening will probably recognize, and just see how you can follow all the rules and still lose.
So let's start with the system itself, LEMORA, because it's not just some simple script. Marcus describes it as having an intelligent aperture.
Which is just a really fancy way of saying it's self-documenting, right? It explains its own decisions.
Pretty much, yeah. It explains itself, and it pushes all of this context into a cloud knowledge graph in Firestore. It's meant to be smart.
And Marcus, he defined these 6 axioms to guarantee it's reliable. Things like no silent failures, explicit state, and the big one for this first bug.
Atomic operations.
Atomic operations. That's a huge pillar of reliable engineering, isn't it? The idea that an action either happens completely or not at all.
No half states. It's like a bank transfer. You don't want the money to leave your account but never arrive at its destination. You need the whole thing to be atomic. Marcus was obsessed with this idea.
But Elera pulls out a napkin, and I love that it's always a napkin in these stories.
Always.
And she draws a diagram that just proves him wrong. So let's get into the code. How did Marcus actually implement this idea of atomicity?
Well, he used a pretty standard tool called flock. It's a file locking mechanism in Bash. The logic is simple. Before I write to the state file, I lock it.
Okay.
And if anyone else tries to write, they have to wait until I'm done and unlock it.
That sounds reasonable. I mean, if the file's locked, you can't have 2 processes writing over each other and corrupting the data, so where's the flaw?
The flaw is in the scope of that lock. See, Elera points out that LEMORA runs health checks in parallel from 7 different regions at once.
Okay, so you have 7 processes all trying to update the system's health status.
Exactly. So imagine 3 of them. Let's call them A, B, and C start at the exact same time. The operation is always read the current state, modify the data in memory, and then write the new data back to the file.
I think I see where this is going. It's the classic check then act problem.
You got it. Process A, B, and C all read the file at the very beginning. Let's say the file's totally empty, it's just health. They all pull that empty state into their memory.
And because reading isn't locked, or maybe the lock only wraps the right part of the operation.
That's the trap. Even if they lock the file perfectly during the write, the damage is already done. Process A gets the log, writes its update, and then leaves. The file now has A's data in it.
But process B is still holding on to that original empty state it read earlier.
Right, so when process B finally gets the lock, it just overwrites everything process A did with its own version. It's completely oblivious that the world has changed since it first read the file.
Last one to write wins. Or I guess makes everyone else lose.
Exactly. Elera calls it the last write wins scenario. And she makes this brilliant distinction here. She tells him it is file level atomic, but not data level atomic.
Wow, that is such a crucial distinction. The file system did its job, the bytes aren't corrupted, but the application's logic totally failed because the abstraction was just at the wrong layer.
He was protecting the file, but he wasn't protecting the integrity of the data inside the file.
He thought he was building a bank vault, but he really just put a do not disturb sign on the door. It stops people from coming in at the same time, but it doesn't stop them from acting on bad information they got before they walked in.
And this wasn't just a one-off thing. Elera sees a pattern here across all 7 bugs.
A deeper disease in the system.
She calls them data transformation bugs. And she uses this term that I know you're familiar with from electrical engineering, impedance mismatch.
Right. In physics, impedance mismatch causes signal loss when energy moves between two different mediums, like light bending when it hits water.
It's the same thing with data. In LEMORA, data is constantly being moved between different formats. It starts as a bash variable, then it's turned into JSON, then it's escaped to be put inside more JSON, and then it's sent off to Firestore.
That's serialization hell. I mean, every time you convert data from one format to another, you're risking a leak. You're risking a loss of fidelity.
Or you break the structure completely. Elera points to this one specific line of code with JQ, the JSON tool. Marcus was trying to stuff some raw context, like a log message, into a bigger JSON document.
And he was using string escaping to do it.
He was. The code was something like prim% contextra JQ baliases. He was trying to turn a raw string into a safe JSON string that he could just inject.
Oh, I've seen that go wrong so many times. You think you've caught all the special characters, the quotes, the backslashes.
And then something totally unexpected comes through. A new line character. A weird emoji. Something that breaks the syntax of the container JSON.
So because the implementation relied on string mashing instead of, structured object building, the whole system was just fragile. One weird character in a log could crash the whole deployment.
And that brings us to the small stuff. The bug that I actually laughed at when I read it. The UOD collision.
This is the random bug, isn't it?
It is. Marcus needed a unique ID for every deployment, so you just used the built-in random variable in Bash.
And Elera just looks at him and asks,
Do you know how many bits that is?
It's 15 bits, which is what, about 32,000 possible numbers?
32,767, yeah.
Which is tiny.
For a global deployment system, that's nothing.
He was combining it with a timestamp, thinking that would be enough to make it unique. But Elera calls it collision city. If you have multiple deployments starting in the same second, and you only have 32,000 random numbers to pick from.
You are statistically guaranteed to get duplicates. It's the birthday paradox on steroids.
Totally. And again, look at the pattern. It's a transformation failure. He transformed the requirement, I need a unique ID, into the implementation timestamp plus random. The implementation just couldn't support the weight of the requirement.
He didn't have enough entropy, not enough randomness in the material he was using.
Which brings us to, I think, the most painful critique of all. The one that made Marcus put his head in his hands.
The violation of his very first, most sacred axiom.
No silent failures.
Oof. This one hurts because it's just so ironic. The design goal is explicitly, tell me when something breaks. But the code did the exact opposite. Elera points to a line right after a call to log something to Firestore. It's true.
Okay, so for anyone who doesn't live in Bash, that is the OR operator. It says run the first command, and if it fails, then run the second command.
And the true command just returns success, no matter what.
So it's basically telling the script, if the logging fails, just pretend it didn't. Move on, don't crash.
Yep. Force a success code and keep going.
Now, to play devil's advocate for Marcus here for a second, I get the impulse. It's a deployment system. Do you really want the whole production rollout to fail? Just because your logging server is having a bad day?
And that was his exact defense. He wanted the system to be defensive, to be resilient. He thought, why should a secondary system kill the primary mission?
But in doing that, he blinded himself.
He lobotomized the system. By swallowing that error code, he made it impossible for the system to ever know it was failing. He violated no silent failures to try to achieve uptime, but he ended up with neither.
It's that gap again between I want this system to be resilient and I've actually made this system a liar.
Liar is a strong word, but it fits. The system reports success when it's actually failing. And that creates a false reality for everyone. This gets us to the philosophical core of the whole thing. We're not just talking about bad code anymore. We're talking about abstraction layers.
Right. This is where Elera uses that analogy about building a bridge, which I found so helpful.
It's the perfect visualization. She makes a distinction between an architectural axiom and interior axiom.
Walk us through that.
Okay, so the architectural axiom is the high-level design. It's the physics. The bridge must support a 100-ton load.
Mm.
That describes the behavior. That's what Marcus was doing with his 6 rules.
The math works out perfectly on the whiteboard.
But then you have the material axiom, and that's the steel we use must not have any air bubbles. That is an implementation detail. It's about the physical substance you're building with.
And her point is, if steel has air bubbles, it doesn't matter how perfect your math is, the bridge is going to collapse.
Precisely. Marcus had perfect architectural axioms, but he had 0 material axioms. He had no rules for how the bash code or the JSON or the data pipes should actually behave in the real world.
He just assumed the steel of his code was perfect, but it was full of air bubbles, like true and random.
So the solution isn't just to go fix the bugs. That's just playing whack-a-mole. The real solution is to create a new set of axioms for the implementation layer itself.
What does that actually look like, though? It sounds like we're just adding more rules.
We are, but they're rules for the plumbing. Elera suggests 3 really good ones. First, idempotent transformations.
Meaning, if you do the same operation twice, you get the same result. You don't corrupt the state.
Right. Second, validated transformations. Don't just assume your JQ command worked. Check the output. Verify the steel before you pour the concrete.
Makes sense. And the third?
Commutative updates. This is what solves that race condition we started with. It means designing the system so parallel updates can be merged without data loss, no matter what order they arrive in.
So instead of just trying to lock the door, you redesign the room so multiple people can work in there at the same time without bumping into each other.
Exactly. You change the nature of the plumbing to match the fluidity of the data.
Which brings us to the end of the story. Because Elera didn't just critique the system and then leave.
Of course not. She's ops. She probably wrote the fix while he was ordering appetizers.
She walks out of the sushi restaurant with him and reveals she's already written V4.3.1.
And the fixes she made are just a masterclass in this material axiom idea. The race condition with flaw. How does she solve that?
She just abandoned that whole read, modify, write pattern. She switched to a write, merge pattern. Every process writes its little update to its own unique temporary file.
Ah, so no one is overwriting anyone else.
Exactly. Then a separate atomic process comes along and safely merges all those temp files together.
No data loss. Smart. And the JSON escaping nightmare.
She stopped doing it. She used JKey to build the entire JSON object from scratch, let the tool handle the structure.
So instead of gluing a broken base together, she's molding the clay from the start.
That's a great way to put it. And the silent failures.
She just deleted the true.
She just got rid of it.
Got rid of it and replaced it with specific error handling. If Firestore fails, you catch that specific error, log it somewhere else, and then you can decide if the deployment should continue.
So she brought nuance back. It's not just crash or ignore, it's acknowledge and handle.
And finally, the UIDs. She ditched random and put in a proper fallback to diva random or a real diva rad generator. She just increased the entropy.
She got better steel.
She got better steel.
You know, what I love about the ending is Marcus's reaction. In so many of these stories, the architect would get defensive or angry, but he has this moment of, like, genuine realization.
He does. He gets that his big ideas, the intelligent aperture, the cloud knowledge graph, they weren't wrong. They were genius. But, as Elera says, in maybe the best line of the whole piece,
Ideas without engineering are dreams.
but engineering without ideas is just hacky.
Engineering without ideas is hacky. That needs to be on a t-shirt.
It's the perfect synthesis, right? You need the vision, or you're just writing scripts that go nowhere. But you also need the person who knows that random is only 15 bits, or your vision is going to collapse under its own weight.
It totally recontextualizes what a bug even is. These weren't failures of his vision, they were failures of translation. By fixing the plumbing, Elera didn't change his design, she actually honored it.
She made the system finally live up to the promises he made on the whiteboard. The bug fix isn't just a patch, it's an act of alignment, aligning the implementation with the intent.
The story ends with them just walking to the subway. It's quiet. And Marcus realizes he wasn't just building a deployment tool, he was getting a masterclass in abstraction.
And Elera leaves him with that final thought. Axioms all the way down, or at least down enough.
Down enough. I love that. That's the pragmatic part. You can't model every single electron moving through the CPU.
No, madness lies that way. But you have to go deeper than the whiteboard. You have to go down to the layer where the failures are actually happening. You have to understand your materials.
It's just such a compelling reminder for anyone who builds things. We all fall in love with our models, our perfect designs.
The happy path where everything works. But reality is messy. It's race conditions and network timeouts and limited entropy.
And reality is a sushi restaurant where your co-founder tells you your baby is ugly, but then helps you fix it.
Which is much better than finding out during a production outage on Black Friday.
Amen to that. So as we wrap up this deep dive, it really leaves us with a provocative question for you, the listener.
It does. We all have systems in our work or even in our lives that we think are perfectly designed.
Mhm.
We have the rules, we have the intent, but where's your implementation gap?
How many perfect designs in your life? A software project, a business process, maybe even a personal habit. How many are failing right now? Not because the idea is wrong.
But because of some plumbing issue, some material flaw in the implementation that you just haven't looked at closely enough.
It's worth debugging.
It certainly is. Thanks for listening to this deep dive.
We'll catch you next time.